Live போயிடுச்சு சார்.
லைவ் ஸ்ட்ரீம் பண்ண ஸ்டார்ட் பண்ணிருக்கேன்.
Yes. Okay. Very good evening to all. I welcome you all for this Professor SVM Satyanarayana Memorial Lecture 4. So this is a lecture that we start from this year, the first lecture, and we wholeheartedly welcome our dear Professor, Satya's friend, Professor S. Sivakumar, Division of Sciences, Kriya University. He kindly agreed to give this lecture this year 2025. And I very happy to see our senior Sunday class student and present Sunday class students, and you enthusiastically joined here. And you all know that the last year we conducted 3 lectures. The first lecture started by the Deepak Dar and the second lecture Sunil Mugi. So we had 3 eminent speakers, and it was well appreciated by the physics community in Tamil Nadu, and also lot of views came in YouTube. You can watch later also. So to continue that legacy of Satya sir, the main purpose of starting this lecture series is we want to spread Satya sir's word, Satya sir's commitment and legacy and the physics teaching importance. So we plan to do in future also. In this great occasion, we have so many old Sunday class students and present Sunday class students. The main plan of this today's lecture is, first, a Sunday student will talk about his experiences and the intention of this lecture series. And secondly, Dr. Kamal will play a short video about Satya sir. And third, there is a introduction about the today's speaker, Professor S. Sivakumar. Then the lecture will start. So around 1 to 1.5 hours lecture will go. He will be today presenting very exciting topic of quantum computing. Then after the talk, the question and answer sessions. So I request all the participants, you hold on while the talk is going on, you hold on the questions. You can type the questions in the Zoom, or those who are watching in the YouTube live, you can type your question in the YouTube live. So all the questions will be taken up and we will give it to our speaker and he will answer one by one. So please maintain while lecture is going on. Please don't scribble anything in the screen. Please don't do any annotate. Also, you please switch off the your video so that we can save the data, so that the audio also will be very clear. So without any further delay, I invite one of our promising Sunday class student, Dr. Rajmohan, who is now assistant professor in Gandhigram Rural University. So he will give a brief note about this today event. Over to Rajmohan.
Thank you, Joseph. Good evening, everyone. As I explained by Joseph, I am a Sunday class student. At present, I'm working as assistant professor in the Department of Physics at Gandhigram Rural University. Actually, I am a Sunday class student from 2010 to 2012, almost 3 years, along with 2 of my student friends, Dr. Praveen and Vignesh. So actually, we travel from Gandhigram to Chennai around 450 kilometers every week, and return back once again 450 kilometers, around 900 kilometers. Actually, you can check our attendance, it should be 100%. We 3 were first generation rural area student and also very poor background. We are not affordable to pay any amount to attend any coaching classes. Because of this Sunday class, I could clear gate and set. Praveen could clear gate, set, CSIR and just. Now at present he is working as a lecturer at Government Polytechnic College. Vignesh is another person from very poor background. He qualified gate as well as set. Now at present he is working as St. Joseph's University, Bangalore. At present he is at German. We 3 were highly benefited only because of Sunday class. So let me thank Professor S.M. Satya sir for this Sunday class. So at this juncture, I should thank my teachers, SVM Satyanarayana, Professor Rajasekaran, and Professor H.S. Mani, Dr. Naina Mohammed, Dr. Tangadurai, and Pon Murugan. These are my teachers during the Sunday class. The beauty of the Sunday class is all the teachers are always go to extra mile to help students on problem solving. I could see the dedication, enthusiasm, and patience from all the teachers. Now let me welcome you all for this Professor SVM Satyanarayana Memorial Lecture on Quantum Computing. And thank you all.
Thank you, Raj Mohan. So now I invite Dr. Kamal to play a short video about Satyanarayana, sir.
Visible?
Yeah, I think, yes, visible, sir. Yes. Sound is not heard.
It's heard, sir. It's heard.
Okay.
But if it is satisfying only 1, 2, and 3, then that is called a monoid. These are just names for they exist, so I am writing. And if it satisfies 1, 2, 3, and 4, it's called a group. And if you may want to call it as a 5, if it satisfies 1, 2, 3, 4, and 5, it's called an abelian group. Learning science is not about answering a question, but it is a training to question the answers. I believe that we must judge the progress of a student not on the basis of answers that he writes in the examination, but only on the basis of questions that he asks in the class. Because the ability of questioning gives us a window to judge the understanding ability of the student. So I think, in my opinion, the first and important aspect of teaching is to make them ask questions. Now, this is a very, very tough task. We have a group of heterogeneous people with different backgrounds, different knowledge initial states, and we cannot easily make everyone to come out in open and ask questions. There will be a lot of inhibitions, there will be fear, there will be a doubt that others will ridicule, all these problems will be there. But we have to deal with all of them, we have to live with all of them, and yet make some progress in terms of training them to ask questions. This is the only way to really judge whether someone is making a progress or not. Second important thing is how best you teach does not depend on you alone. It depends on you as well as the given set of students. So your teaching should be a function of the group who is attending. Suppose I learnt group theory I teach everywhere in the same fashion, but the audience in one place may be different from the audience in another place. So your teaching, the content, the method of presenting, and the problems that you choose, the way you present it, everything has to be a function of the set of students or the audience whom you are addressing. So if the audience are ready to receive, then only they will receive. How much ever clear presentation that you make, if the audience have no readiness, then it all goes waste. Now, for that purpose, what we have to do is you have to do an initial exercise of making the audience ready for what you have to teach. Okay, so how to make audience ready is another technical aspect which we will discuss. So you have to have a readiness. If you are not ready to receive, you will not receive.
Joseph?
Yeah. So thank you, thank you, Dr. Kamal. Now I invite Mr. Ritish Bharat to introduce.
Good evening, everyone. Dear students, distinguished faculty and honored guests, good evening, everyone, and a very warm welcome to the Professor Satyanarayana online memorial lecture series in physics. We are truly honored to have you with us this evening. It is my great privilege and pleasure to extend a heartfelt welcome to our esteemed guest, Professor Sivakumar Srinivasan, Professor and Dean Research, Division of Sciences, Kriya University. Professor Sivakumar has devoted his career to advancing our understanding of both quantum and classical dynamics as well as statistical physics. He began his journey as an undergraduate at Pundi Pushpam College in Tanjavur. He then pursued both his master's and doctoral studies at the prestigious Indian Institute of Technology, Madras, where he built a solid foundation in the fundamentals of physics. Following his time at IIT Madras, he joined the Department of Atomic Energy as a scientist, where for over 2 decades he tackled problems of critical national importance. His pioneering work, spanning both theoretical development and experimental application, has played a vital role in the design and operation of research reactors at the Indira Gandhi Center for Atomic Research in Kalpaka. Throughout his career, Professor Sivakumar research has evolved from exploring coherent states, atom-field interactions, and quantum entanglement to leading-edge investigations at the nexus of quantum optics and quantum information. In particular, his work on coupled cavity systems is helping to identify real-world platforms for the future of quantum technology, and his studies of entanglement and condensed matter systems continue to open new avenues of inquiry. Beyond his research, Professor Sivakumar is a passionate educator. With 2 decades of teaching experience at institutions including the Homi Bhabha National Institute, the Chennai Mathematical Institute, and now at Kriya University, he has inspired countless undergraduates, postgraduates, and research scholars to pursue their own paths in physics. Many of his mentees have gone on to distinguish such careers, a testament to his dedication as a mentor and a teacher. It is also fitting to acknowledge that Professor Sivakumar and Professor SVM Satyanarayana shared a long-standing friendship dating back to their days together at the Indira Gandhi Center for Atomic Research, a bond rooted in mutual respect and a shared passion for discovery. Let us extend a heartfelt welcome to Professor Sivakumar as we begin the Memorial Lecture Series in Physics. We look forward to benefiting from his insights today and thank him for sharing his time and expertise with us. Thank you, sir.
Thank you, Ritish. So with great pride, and I invite Professor Sivakumar to start his lecture.
The outset, let me thank Ritish for that wonderful introduction, very generous introduction. Also to Joseph Prabhakar for this invitation. So let me start making the presentation. I will share the screen. Let me just know whether it works.
Yes, sir. Your screen is visible. You can make a presentation mode.
That's what I'm trying.
Yeah.
Is it full screen now?
Yes, sir. Yes, sir. Yes, sir.
Okay. Thank you very much. So rightfully so, APT Tunes, the official in-house magazine of the Kerala Physics Teachers Association, brought out an issue in honor of Professor SVM Satyanarayana. And I do not know what to say, whether it was required that unfortunately I had to write an article on my friend Satya in that. It was very unexpected, very shocking that we would lose him. And yeah, it's still a very shocking moment for all of us. And when I started writing it, but so many thoughts crisscrossed my mind as to, try to characterize what Satya was. And finally, I thought two sentences from the article that I wrote probably summarized what Satya was to all of us. So he was called Satya by all of us, especially his colleagues, and Satya Sar by his students. Important point is he was essentially almost single-handedly responsible for so many students who took to research post their attending Sunday classes. It may not be an overstatement if I say that almost every university in the state has at least one of Satya's students. And for his contributions in changing the way or even the lives of these students, I'm sure he will live in their memories forever. And as an excellent colleague and friend to many of us, I'm sure he would live in our memories forever, as long as we are alive. So with these few words about my friend Satya, let me start talking about quantum computing. It's also a field that was very close to Satya's heart. And maybe I should also begin with a note of apology that I couldn't really give a talk in the earlier years, though Joseph had been asking me for almost 2 years now. And finally, it happened that this year I could give. And I'm sorry about the delay. I should have done it because it was, after all, to remember Satya. Is this okay? Are you able to see the next page?
Yes, sir. Yes, sir.
Okay, thanks. So quantum computers, the subtitle of this talk is the next revolution in computing with a question mark. And let us see whether we are convinced at the end of the talk, the next revolution is indeed happening. So a brief point that we will touch upon in this lecture are listed here for your view. And we will not be going in great depth in any of these things because of the time required to convey anything substantial in any of these topics will be few hours. Since the whole talk is going to be for slightly more than an hour, I will restrict myself to the very basics that you should know so that you can pick up a book on your own and start learning this field by yourself. So as you all may know, this year 2025 is the International Year of Quantum Science and Technology. And there is a mission for this declaration by UN. That is what I have highlighted here in red, helping others to learn more about quantum on the centennial occasion, or simply taking the time to learn more about it themselves. If either of these two is what we are looking for. I hope this lecture, because it's fairly simple to understand, should enable you to take up either learning more about it by yourself or helping others to learn. Okay, let us get into some mild details. Before we actually start discussing quantum computing, let us try to recall some very basic facts about classical computing. Since this is something that might be familiar to many of you, I will rush through, and when we enter quantum computing discussion, I will slow down a bit. So I'm just giving you one of the computers called UNIVAC, which is actually an acronym for Universal Automatic Computer. And here on the right, I have given you the biodata of this computer. It was built in 1951. And you can note its weight is 7.6 tons. It consumed 125 kilowatts of power. And it was, of course, operating with vacuum tubes. Important point is that it was doing about 2,000 operations per second. Okay. Now, what is it that we have currently? We have a Frontier, a supercomputer at the Department of Energy at ORNL, and it can does number crunching at the rate of 11.11 flops, that is floating point operations per second, which is about 10 power 18 operations per second. So from 10 power 3 operations per second in 1951, we have gone to 10 power 18 operations per second now, okay? And of course, this computer weighs nearly 270 tons, and it contains about 40,000 processors and so on and so forth. It consumes huge power, about 350 horsepower pumps, and that's enormously high power. So while we are able to achieve very high speeds with this computing, there is something common about UNIVAC, which could do only about 2,000 operations per second, and Frontier, which can do about 10 power 18 operations per second. Okay. Just for comparison, I have given you a chart here. So the Apollo 11 guidance computer, which was carried by that rocket, which landed men on moon, that was doing about 12,000 operations per second. Cray-2, which was one of the most talked about supercomputers in the 80s, that could do about 1.9 billion operations per second. If you are a owner of an Apple iPhone 12, then this will do 11 trillion operations per second. You see, the current day mobile phones are far superior compared to the so-called supercomputer of yesteryears. So what we notice is, though the number of or the power of these mobiles have become much more compared to the supercomputers of the previous years, the sizes of these mobile phones are very small. You can hold it in your hand, whereas a Cray supercomputer was actually occupying a big room. So with all these supercomputers, very advanced, even the Frontier machine that I talked about from ORNL, what is it that one could do with these computers? You can simulate about the behavior of 40,000 electrons in a crystal, or you can look for weather pattern with a grid size of about 3 kilometers by 3 kilometers. But very often, 40,000 describing or understanding the behavior of 40,000 electrons may not be sufficient at times. And if you want to go beyond, the current day computers are not going to be very useful to you. Okay. And in order to understand why these computers have this limitation, let us try to start with something very basic. So we all know that we use a decimal system, which essentially means you can use your 10 fingers to count. And you can also have a system based on just one hand, let us say 5 fingers. Then after 4, it will be 1 0. What does 1 0 mean? I have used the one hand fully. All the 5 fingers have been used, and the next round of counting with fingers is yet to start. Therefore, 0, 1 0. Then I use one hand already. I have used once, and again I'm using one finger from the next round. Therefore, it is 1 1 1 2 1 3 1 4, and I have used it twice. That is 5 fingers once, 5 fingers twice. Therefore, it is 2 0. So this is base 5. You can apply the same logic to base 10. You will be ending up with the familiar decimal system. Okay. But you can also do it with just 2 fingers, 0 for 1 finger and 1 for 1 finger. If we have used both of them, then the next term will be 1 0. So what does this number 10 in binary mean? It stands for number 2 in base 5 or number 2 in base 10. Okay. Now, what about a number something here? Let us say 110. Sorry, 110. That will correspond to 11 in base 5 and 6 in base 10. Okay. So this conversion is something I'm sure familiar to all of you. So given a number in one base, you can always switch over to another base very easily. Okay. Now, why binary sequence? That's because binary digit, because it has only 2 states, 0 and 1, it is very easy to represent using technologies. That's one of the ease of representing them is one of the major reasons why binary picked up. Okay. Now, how do computers actually understand even language? Well, everything is written in terms of 0 and 1. What I've given you is an example of what we can call an alphabet chart for computers. I'm going to say my alphabet has only 2 letters, capital A, capital B. So I'm going to represent capital A as 111, which I can represent using an electronic gadget, let us say, and B as 110. And I have listed a list of symbols here, and you have given 3 digits for each of these symbols. Now I have got a binary sequence on the right, which is given here. And the condition that I have is read this binary sequence in packets of 3 bits. So first 3, next 3, next 3, and so on and so forth. Once we do that, we will be able to identify what the sequence stands for. So in this case, I have indicated the first 3 in blue, next 3 in black, subsequent 3 in blue, and so on and so forth. Now you can easily use the dictionary given to you on the left and understand that this number sequence, that is the binary digit sequence, stands for Baba space 1 2 dot. Okay. Now you see a sequence of numbers can be used to represent the alphabet that you use to express yourself in as language. Okay. So what is the only condition? Read in packets of 3 bits. So this is the idea behind the ASCII code that you would come across when you learn computer science, which has got more than 3. 3 is obviously not adequate to represent all possible alphabet that we use, uppercase, lowercase, and every symbol that you see on the keyboard. So, but you can have a larger representation, and this is the idea, key idea behind that. That is, you represent each symbol by same length sequence, binary sequence. Okay. So, as I told you earlier, binary representation is simple and general enough to represent information, and technological implementation is not difficult. So that is the great attraction for using binary sequence. Okay. So information is physical is the next key idea that you should keep in mind, because after all, information is not floating around in space. It has to be carried by some gadget. It could be a transistor, it could be the on-off condition of a bulb, or you can simply have a bunch of students who will raise their right hand to represent 0 and the left hand to represent 1 and so on. Of course, with the condition that they can raise only one hand at a time. When one hand is up, the other hand has to be down. Okay. But that's not the way we use, we operate our computers. We have very minute but extremely efficient gadgets called CMOS, complementary metal oxide semiconductor devices, and they can exist in low current status or high current status. So you call low current as 0 and high current as 1. And therefore, by having a sequence of these gadgets, you will be able to represent any sequence. And you can also change a low current CMOS system can be changed to a high current CMOS system by a signal, and therefore essentially you are changing the sequence. Okay. The other thing that I would like you to notice is, if I measure the current in the CMOS system to ascertain whether it is in 0 or 1, that is not going to affect the state of the system. Okay. So this is typically the way you will represent bits. Let us say 0 at the top of the box and 1 at the bottom of the box, and you have something called gates. What do gates do? Gates transform bits. When I say transform, it will convert 0 to 1 or 1 to 0 if you have just 1 bit. So what I have given here is the example of a NOT gate. It converts a CMOS system in 0 to CMOS system in 1 and vice versa. At times, you also need gates with 2 inputs and 1 output. For instance, an OR gate. So if you have 2 zeros, the output will be 0. If you have a 0 and 1, the output will be 1, and so on and so forth. Okay. Here is a list of gates that you will come across. So you have NOT gate, AND gate, or XOR, and so on and so forth. And by and large, all the computer systems that you come across, including your mobiles, they all will have these kind of circuits integrated, and that's how they operate on information that you feed in the form of bits, and they produce results. What is important to understand here is, to understand these semiconductor devices, quantum theory is absolutely essential. However, we don't call these computers as quantum computers, they are still classical computers. It is only speed and ease of operation that is a big advantage for using semiconductor devices. You could have very well done it with, as I told you, students raising their hands, right hand and left hand to do this part. That will be slow, it will be consuming a lot of energy, but there is no problem in sort of mimicking the behavior of a classical computer with any other system that has got just two levels. You can switch off and switch on light. When the light is on, call it 1. When the light is off, call it 0. You could have done that as well. Okay, so these are still not quantum computers, though at the level of understanding how these circuits work, you definitely need quantum theory. Okay, here is one gate. Probably this may not be really required for this talk, but I would like you to notice this. This is called Toffoli gate. The important thing about Toffoli gate is the input and output are perfectly correlated, so that you can go from input to output, or if you give me the output, I can tell you things. For instance, if you go to NOT gate, if I tell you the output is 1, you can immediately say the input must be 0. Okay. On the other hand, if I tell you in an OR gate, the output is 1, the input could have been 0, 1, 1, 0, 1, 1. There is no unique way to identify the input from the output. When that is possible, you call it a reversible gate, and a Toffoli gate is a reversible gate. What is the advantage of this Toffoli gate? You can actually create an AND gate out of Toffoli gate, and computer theorists will tell you that NAND gate is an important part of what we call a universal set of gates. NAND gate and a few other gates like fan out and so on and so forth, you will be able to produce every other gate that you wish to construct. Okay. Now, I told you that miniaturization has happened because we had a computer which was occupying almost a full room like UNIVAC. And from there we have gone to, let us say, gray computer, and subsequently your mobile phones, which are much more powerful compared to UNIVAC, but occupies much smaller space. You can actually hold it in your hand. Okay? The reason for that is the number of gadgets, the so-called transistors that you can pack on so-called integrated circuit. Okay? So Moore's law is an estimate of how often the number of transistors on, let us say, roughly 1 square inch grows as a function of year. He said every 2 years it doubles. Okay. Now, in somewhere in 1970, we started with about 1,000, let us say, transistors on an IC. In about 2020, we have 5 into 10 power 10 transistors on an IC of the same area. Okay. Now you see the amount of package that has happened. All this is because of development in technology, and this is what has really helped us to reduce the size of these machines, make them more powerful, and also very energy efficient. So just to tell you, in 1960s, number of atoms required for one transistor is 10 power 17. In 2000, with the 10 power 8 atoms, you can make a transistor. Okay, and energy consumption is 1970s, it was 100 picojoules. Now it is 0.1 picojoules, 1,000 times smaller energy per operation. So that is the kind of energy efficiency that has been built into this. Okay, and is it possible to pack more and more? If the current technology is what you are relying on, it will not be possible beyond a point, because when the size becomes really small, quantum effects will become manifest, and you will not have the kind of deterministic evolution of these gates anymore. And therefore, the current architecture may not be helpful. Now, there is the fact that you will not be able to pack more, and there is a limitation on what these computers can do, is both good and bad. Let me first start with the why is it good not to have powerful computers, and this is essentially related to what is called crypto system. So whenever we send messages across the internet, our messages are encoded so that others will not be able to figure out what is it that you are sort of communicating on the internet. This is done by something called encrypting, and this encrypting depends essentially on one key factor, namely, it is very difficult to find the prime factors of a large number. Okay, So as you know, prime factors mean, for instance, if we take the number 10, 2 into 5 is the prime factorization. 2 is a prime number, 5 is a prime number. If you take 68, I have given it to you here, 2 into 2 into 17, that is the prime factorization. For small numbers, it is very easy to do, but when the number size becomes very, very large, let us say 1040 digits or 2000 digits, then it really becomes very difficult to figure out what are those 2 or 3. Yes, usually they talk about 2 prime numbers that you need, so that when you multiply them, you will be able to produce the number given. So on the right, you can see it's a kind of a story on a single core 2.2 gigahertz AMD Opteron processor with the 2 GB RAM. Sieving is a process of finding out these prime factors. That's a mathematical technique. It would have taken about 1500 years. Okay. That's the kind of time that you need if you want to really factor this. The fact that you need such a large time is actually the safety mechanism behind this cryptography. Remember, it is not that it is impossible to break this. You can, given sufficient time and resources, you can. But it takes such a long time that in a meaningful time, let us say a few days or few weeks, you will not be able to do this. Because before that, usually the service providers change the prime number that they use for encoding, and therefore the prime numbers change. Therefore, you have to start with a new analysis. So it is this requirement for a long time to decode or finding out the prime factors. That's actually the safety mechanism in this RSA crypto encryption, which is called RSA. Actually is the first letters of the names of 3 gentlemen who created this: Rivest, Shamir, and Edelman. So this is a good thing that you don't have powerful computers means nobody will be able to sort of figure out or break the code that you are using to encrypt your message. And what is bad about this not having powerful computers? You know that a liquid natural gas is a very costly commodity, and it's an important commodity. Forget about the cost. We should not be wasting it. So what is the best way to transport this from the place where it is produced to the place where it is being used? We have warehouses, storage houses, and so on and so forth. Turns out there are 2 power 10 power 6 ways in which these paths can be drawn. Okay. And the classical computers that we have currently just cannot these many combinations. In fact, just for fun, I have given you, there are about 2 power 270 atoms in the universe. Okay. And where this number of possible paths all over the world, of course, is 2 into 10 power 6. Of course, there are other interesting problems that one can look at. For instance, flight design problems and Boeing aircraft design can involve up to 100,000 variables, and each of these variables have a bunch of, let us say, 10 values each. Then you have essentially 10 power 100,000 possibilities, and which is the best one you may have to design. Obviously, the current day classical computers will not be able to handle this. We have told you 40,000 electrons already. These computers are at their brink of their capability. So bit-based computers are not good enough. So of course, the obvious question would be to ask, can we harness the quantum? Okay. Now let us see what it means to do quantum computing. As I told you, those understanding behavior of semiconductors requires quantum mechanics. These computers are still not quantum computers. They are fundamentally classical computers. Okay. Of course, anything that begins with the, bang in physics has some association with Feynman, and it's so in this case as well. So he wrote a paper simulating physics with computers, where he actually makes a statement, which I have highlighted here in red. It is impossible to represent the results of quantum mechanics, the classical universal device. Okay. So that he has very clear arguments as to why he comes to that conclusion. I'm not presenting those arguments here. It's not immediately relevant to this talk, but it's an important paper that I would think that every one of you should read. Very readable paper, and it's an important paper. Almost at the same time, Yuri Manin, a Russian mathematician, he also came up with the idea that it is actually possible to invoke quantum features to do computation in a very different way and in a more efficient way. Okay. So once again, of course, Feynman from his book, The Character of Physical Law. I will take just this one experiment, which has been designed to contain all the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%. Any other situation in quantum mechanics, it turns out, can always be explained by saying You remember the case of the experiment with the two holes? It's the same thing. So he's essentially referring to the experiment by Young, which all of us are very, very familiar with. That means if you have waves, they propagate in space. When two waves meet in space and time, they can, in principle, show up patterns, which we call interference. Waves always interfere. Whether they will show up a neat pattern or not, that depends on other conditions that they need to satisfy. Okay? But this is essentially a property of a wave. Okay, so this is the experiment that Young, I'm sure all of you would have done at some stage in your education. So you have a light source, it goes through two slits and you capture the outgoing beams on another screen and you will be able to see some kind of a nice pattern if conditions are suitably arranged. Okay, so what we understand is one of the key properties of waves is when two waves can combine to produce a big wave or two waves can combine to annihilate each other. They destroy each other. Okay? So when they combine to become a bigger wave, we call it constructive interference. When they combine to destroy each other, we call it destructive interference. So this is essentially a property of the wave. Okay? But then quantum mechanics tells you there is nothing like property that is strictly that of wave and there is some other property strictly that of particle. And Feynman himself in his book, third volume, in his lectures, talks about doing interference experiment, Young's double slit interference experiment with the bullets. And of course, it's very difficult to do with the bullets, but people have done it with the electrons, people have done it with the C60 molecules and so on and so forth. I'm going just to play a short video of this experiment done with electrons instead of light.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron on the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through a random on either side of the biphasic, thus creating a uniform distribution without any interference when accumulating. Under such conditions, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. This experiment lasted for more than 30 minutes. I have spent a gap. Interference fringes are now clearly visible.
So, of course, I'm sure all of you recognize the character here. So it's a very, very mind-boggling thing. Electrons are particles. One by one, they are captured on the screen. They appear as dots. And if the electrons are, every electron is indeed a particle, you should get a random distribution of points on the screen. But when you collect very many electrons hinging on the screen, that is, you run the experiment very many times and look at the collective results together, then you see that you actually find patterns where electrons are concentrated and where electrons are not present at all. This is what we call an interference pattern. Of course, you can ask why, and at some stage, people get used to say, of course, that's what this cartoon says. Initially, you start asking why, at the end, you say, oh, that's why. So it's a kind of a cartoon. Okay. So now let us talk about qubits. So interference happens even with particles. It's not a property of the classical wave anymore. What interferes, of course, is a question that we need to understand, and it depends on the context. Okay. So what is a qubit? A qubit is a system with the two states. I use this vertical line, a symbol, and an angular bracket to represent quantum state. I'm not really getting into details of quantum states because I need to quickly get into telling you what quantum computers are. But I hope all of you, and since you are all in Satya's class, Sunday classes, I'm sure all of you understand these symbols. So any system with the two states is what we call a qubit. So I'm just representing one of the states as 0 and the other as 1. What are the possible physical systems that could be used as qubits? You can have spin half particles. So spin up is 1, let us say 0, and spin down is 1. That is a possibility. You can, of course, make it the other way. You can say spin up is 1 and spin down is 0. It's up to you, but there are two distinct states and you can call them as 0 and 1 in whichever way you Okay, of course, this is actually a kind of a cartoon, I believe, from one of the Ivy League universities in the US. So they are trying to explain what an electron spin is. Electron spin explained. Imagine a ball that is rotating, except it is not a ball and it is not rotating. That already tells you the difficulty of actually explaining quantum concepts. Okay, so because you don't have anything in classical regime which will sort of mimic quantum properties to all its completeness. So like spin half particles, which has got two levels up and down, you can think of two energy levels in an atomic system. So in an atom, you have two chosen energy levels, and these two levels can be designated as zero. Okay, usually atoms have many levels, but depending on the kind of external perturbation that you switch on, usually a laser field, you will be able to restrict the number of levels that participate in the dynamics, and you can make it possible, it is in fact possible, that just two levels get involved in dynamics, then you have got a qubit using atomic levels. You can use photon polarization, X and Y polarization, for instance, or you can use Josephson junction and as a qubit. Okay, and in fact, the last one, this is Josephson junction, is the most dominant technology as of now. Many of the successful computers, quantum computers that we have, are all based on superconducting qubit based computers. Okay, so the left box is essentially the repetition of the previous slide. Apart from 0 and 1 states, quantum mechanics tells you can also put the system in a superposition of these two states. That is, some complex number times 0 plus another complex number times 1. And this is what we call a quantum superposed state. Okay, it is still a state. It is very difficult to argue saying that it is both 0 and 1. I don't think that's a right statement, or 0 or 1. Both and or are not suitable to this. It's another state. So what is special about this state? The point is stated here. If I make a measurement of whether the state is pointing up or down, then with mod alpha square as the probability, you will find the system in up state after measurement. And with mod beta square probability, we'll find the system in the 1 state after measurement. Therefore, these are all statements about the state of the system after measurement. Prior to the measurement, what was the state? You cannot figure out from this. Okay. Now, this is something that is very distinct from a classical system. A classical bit can be either in 0 or 1. And by assumption, when I find out in which state it is, you are not going to disturb the system. Whereas a quantum mechanical state can be in a superposition. And when I make a measurement, it will end up in one of the two states, 0 and 1. With the certain probabilities associated with these outcomes. Okay. Now it may wonder, if it is not even stable, if there is nothing deterministic about this, is it really possible to use this property to do anything wonderful? Turns out it is possible to do so. And of course, that is the ingenuity of people who created the first set of quantum algorithms. Okay. So you also have a nice mathematical representation of qubits as a point on a sphere, which is called a Bloch sphere. And the north pole of this is the state 0 and south pole is state 1, and every other superposition will be a point on the screen, on the sphere. So on the surface of the sphere, you can represent every other possible superposition. So on making a measurement, the point on the surface of the sphere moves to either north pole or south pole, depending on whether it is collapsing to state 0 or state 1. Okay. Now let us introduce a few more symbols that will be useful. So suppose I have got 2 qubits, okay, not 1 qubit, but 2 qubits. Let us say 2 spin half particles, and both of them are in spin 0 state. Let us say up spin, both are in up spin. I represent it as 0, 0. Okay, to say the first spin is in state 0, the second spin is in state 0. And that means both are spin up. What is the classical bit equivalent? Of course, you can have both the CMOS systems in 0, 0. You can have 1, 1. The second line of this table, and the corresponding, of course, the interpretation is both the qubits are in state 1. The classical bit will be both 1. Now, the third line talks about the first qubit in a superposition 0 plus 1. There is an overall normalization constant. In this lecture, I'm not actually plugging in those normalization constant, but imagine that all these states are normalized. And the second qubit is in the state 0. It is possible to interpret what is the state of the first qubit and what is the state of the second qubit. So the first qubit is in a superposition. The second qubit is in state 0. For this, there is no classical analog, because the second qubit, of course, 0 state can be realized in a classical bit. The first bit, which is in a superposition, cannot be realized in a classical bit. The fourth, the last line is even more intriguing. So I have got a superposition of up and down spins, and it is not possible to say in which state the first spin is or in which state the second spin is. The whole system is in a superposition, but individual spins are not in any particular superposition. So even within quantum mechanics, you cannot assign a state to individual particles. Of course, you just cannot have this kind of a situation in classical physics. I'm restricting my attention to classical physics of particles, not waves. Okay. Now, Schrödinger dramatized the last state, that is, yes, situation where you can assign a state to the whole system but not to the individual system by his famous Schrödinger's cat. I will briefly describe what it is. So you have got a radioactive material somewhere, and the radioactive material can decay anytime, and inside there is a cat which is awake. And whenever this radioactive material decays, it will sort of release, let us say, a kind of a sedative, a chloroform, let us say, chloroform is released, and therefore the cat is put to sleep there. Okay. So, and you put all these things in a box and shut it. Now you ask, what is the state of the cat? Of course, you will not be able to answer because you do not know whether the radioactive material has decayed or not. So there are two possible situations: an active nucleus, that is, it is yet to decay, and therefore cat is awake because chloroform is not released. Or chloroform, the nucleus might have decayed, chloroform would have been released, and the cat might be sleeping. So you have got two possible states. So quantum mechanics now will tell you it is actually in a superposition of awake cat when the material is active, and a cat which is asleep when the material has decayed. And it is, and I put it in capital letters because, as I told you, in superposition, saying it and or is not really meaningful, but I don't have any other word to express this, therefore I just put an and, but I have capitalized it. I put it in uppercase letters. So in fact, Schrödinger himself says not one, but rather the characteristic of quantum mechanics. So that's what he talks about entanglement. Entanglement is not just one of the properties of quantum systems, but it is the characteristic trait of quantum mechanics. Okay, so what? If it is so very mind-boggling, is it of any use to us at all? Now I'll argue a simple case where entanglement can be used as a resource. This is a game that you are going to play. Not even a game, it's kind of an arrangement, I should say. Let us say I have two persons, A and B, you and your friend, and you each have a coin. One side you have head and the other side you have tail. And you have to transmit these coins to exchange information. Okay. So A sends her coin to B, and depending on A's choice and her own coin, B will carry out some act. Okay. If both of them have head, that is, A sends the coin to B and B finds her coin is head and A's coin is head, then B will go to A. So that is the agreement. And of course, all the three other possibilities I have written down: H, 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 T, T, H, T, T. Okay. Now A wants to make any one of the four choices. Is it possible for A to do it with this? A can send H, in which case only A and B are possible. A can send tail, that is a coin with the tail on it. In that case, only C and D are possible. But A wants to exploit all the four choices. Is it possible at all? If you are going to use a classical coin, which can either be in the head state or in tail state, only one of them, not both, then you cannot do this. Okay. Now, is it possible to sort of overcome this difficulty using quantum coin? So that's what I'm trying to do here. So let us say, to begin with, A and B share once again two coins, but these are quantum coins. And I put them in a state which is like your 0, 0 plus 1, 1, so-called entangled state. So A and B have their coins in the state head to head plus tail tail. So individual coins are not in any specific state, but the overall system is in the superposition. Okay. Now A can manipulate only the bit that is available with her. She cannot manipulate the bit available with the B, but A can do whatever she wants with her coin. Okay. So what are the possible things A can do? A can change her coin from T to H and H to T. Both are possible. She can change T to minus T, because remember, we can multiply a state by a complex number alpha and beta in the original definition that I spoke about, which is not possible in a classical system, classical bit system. And she can do H to minus T and then change T to H. So these are the three possible operations. Okay. Now, what are A's maneuvers? A can send their coin asset without making any change, because initially they had it in the superposition H plus T. A can actually perform T to H and H to T, in which case the state will become TH plus HT. And Z she can do, in which case the original state will become HH minus TT. These are all coefficients alpha and beta chosen after the action of these processes X, Z and ZX, and of course the last choice. Now you see I've got 4 different states produced by this action, all done by A only. Like in the classical case, A can choose to send H, A can choose to send T. Now A can make these changes to her coin and ask B to look at what is the state of the whole system. Okay. Now, of course, the agreement here is if B gets a TT plus HH, B will go to A's house and so on and so forth. Now, whatever A wants, now she can in principle communicate all the 4 different or distinct pieces of information using just 2 points, which was not a possibility with the classical points. So it automatically tells you that entanglement is indeed a resource. Entanglement is essentially a quantum property, and entanglement is indeed a resource that could be used. It's called a dense coding technically, but I don't want to get into those details at this stage. Okay. Now, 2 classical bits if you take, of course, you can represent any one of the following 4 numbers, 0, 0, 0, 1, 1, 0, 1, 1, only one of them. Whereas when you have 2 qubits, qubits is the short notation for quantum bits. So you can put all the 4 states in a superposition, and therefore you need 4 complex numbers to represent this A, B, C, D. So there's a simultaneous way you can encode all the 4 possibilities. Okay. And similarly, if you have 3 classical bits, there are 8 possibilities, but at any time, 3 classical bits can represent only one of the 8 possibilities, whereas in the quantum bits case, you can encode all the 8 simultaneously. What you do with all this, that's a different question. And of course, as you all know, when I make a measurement, it will end up in only one of the 8, not all the 8 will be available to you. So the smartness is in devising algorithms so that you can solve problems where the possibility of superposition is exploited, still you get the right answer. Now, what are quantum gates? Like very much like classical gates, quantum gates are physical processes that transform qubits. When I say physical process, it is usually an external field, it could be a radio frequency field or a laser or some other physical process that will change the state of the system. So that's what a quantum gate is all about. Okay. Now, we have got single qubit gates where we change the state of a single qubit. A NOT gate, for instance, will change spin half up to spin down, okay, or spin down to spin up. Acting on a superposition, of course, it will flip as though the first part alone is present. So alpha 0 will be converted to alpha 1, beta 1 will be converted to beta 0. Okay, action on a sum is sum of the actions. That's what it is. That's what linearity is all about. And you have got other kinds of single qubit gates like a Pauli Z, which doesn't do anything to state 0, but it puts a negative sign in front of 1. And on a superposition, you can easily figure out what it should do. And you have another gate called Hadamard gate. Pauli Y is similarly there. Hadamard gate is an important gate. Okay? If it acts on 0, it actually puts it in a superposition 0 plus 1. And if it acts on 1, it puts it in another superposition, which is 0 minus 1. And of course, now it is easy to figure out how it should act on superposition given at the last column of this table. Okay. Now we can combine these gates to construct what is called a quantum circuit. And here is a quantum circuit for you. So I take a qubit in state 1 and allow it to acted upon by the quantum gate X. What does X do? It converts 1 to 0. And that's what you get here. Okay. And on that, I allow Hadamard gate to act, and that becomes 0 plus 1. So this is a simple example of a quantum circuit that you have. And this is a matrix representation of the circuits, not really important for this talk, but just to tell you that in case you want to pursue this further, these things will be very useful. Okay? And what is so special about these quantum gates? Okay. So I'm going to ask a simple question. Is it possible to get a gate, which I call as under root NOT, such that when I operate this gate twice, I should produce a NOT gate? So the question is it possible to have a circuit? When I have this circuit in succession, it should act like a same circuit in succession. It should act like a NOT gate. As you know, NOT gate will classically convert 0 to 1 and 1 to 0. What are the possibilities? For instance, let me say root of NOT acting on 0 gives you 0, root of NOT acting on 1 gives you 1. If this is the way I have designed a circuit, when the circuit acts twice, will it act like a NOT gate? And here is the proof to tell you that it won't act like a. What is the other possibility? root of NOT gate acting on 0, 1 gives you 1, 0. That means root NOT converts 0 to 1 and 1 to 0. It's already acting like a NOT gate, but when it acts twice, will it act like a NOT gate? It's quite obvious. It won't act like a NOT gate. Of course, the other possibilities are root NOT acting on 0 gives you 0, acting on 1 gives you 0, or on both these inputs, it gives you 1 as the output. You can easily check that these things don't work either. So, though I can ask, is there a circuit which when repeated twice will act like a NOT gate? In classical domain, it is simply not possible. You cannot have a under root NOT gate on a single bit, classical bit. Okay. Now, is it possible to do it in quantum mechanics? The answer is yes. Okay, I have not gone into the details of this, but suppose as I told you, all the single qubit gates can be represented by matrices. So, square root of NOT can be represented by a matrix like this. It is easy for you to verify. If I multiply this matrix with itself, it will produce a NOT gate. Okay, that a matrix representing the NOT gate. So, how does root NOT act on state 0? It actually puts it in a superposition of 0 and 1. And root NOT acting on 1, again a superposition. Now you see, without this possibility of superposition and the complex coefficients, it is impossible to construct a under root NOT gate. So already I'm telling you something which is an impossibility in the classical domain, but can be accomplished in quantum domain. Now, of course, 1 qubit gates are not good enough. We need 2 qubit gates if we want to do anything meaningful. And here is an important 2 qubit NOT gate. It's called a C NOT gate, controlled NOT gate. And I have given you the outputs here. When I have got 2 inputs here, C and T. If the input C is in 0 and input T is in 0, that is both are in 0 state, the output will be 0, 0. If the input is 0, T is 0, one of them is, the first one is 0, the second one is 1, it remains unaffected. However, when the first one is 1, the second bit is flipped. When the first one is 0 and second one is 0, it becomes 1, 1. When the first one is 1, second one is 1, it becomes 1, 0. Okay. So this is the control NOT. That is, if the control bit is in state 1, it flips the state of the second bit. Therefore, it's a controlled NOT gate. And this is a very, very useful gate as we can see. Okay. Now, I'm just making a quantum circuit here. So the controlled NOT gate is here with this plus sign. And before that, I put a Hadamard gate. If you remember, Hadamard gate will put 1 and 0 in superposition, 0 plus 1 and 0 minus 1. Okay. So I start with the state 0 and 0. That is, first qubit is in state 0, second qubit is in 0, and I allow it to go through this quantum circuit. You will end up with 0, 0 plus 1, 1, which is like your TT plus H. Okay. And now you can change the possible inputs to the system, and you can have 0, 0, 0, 1, 1, 0, 1, 1, and you will end up with 4 different states. Now, this state is called B0 for the simple reason it is obtained by the action of this circuit on 0, 0, which is the binary representation for number 0. And 0, 1 is the binary representation for number 1, and so on and so forth. And this is the binary 1, 1 is the binary representation for 3. Therefore, I call it state 3. These states are called Bell states. Okay, it was sort of devised in the context of experimentally realizing or a situation to prove or disprove Bell's inequalities, and these are called Bell states. What is nice about this circuit? You can now write a reverse of this circuit. Now, if you see on the input, Hadamard gate acts first and then the C NOT gate. Now, let us say I get C NOT gate to act first and then the Hadamard gate, and feed these Bell states as inputs, it will produce the original input as the output, 0, 0, 0, 1, 0, 0. Okay. So you can undo the effect of this circuit, H followed by C naught, by this circuit where H comes after C naught. Okay. Put together, it will be like an identity operation. So we have talked about the qubits, we have talked about the quantum gates, and the quantum computer is essentially integration of large number of quantum gates. That's what it is. So very much like classical computer. And now what are quantum algorithms? Quantum algorithm, as you know, algorithm by definition is simply a sequence of logically connected steps which will help you to solve problems. And it is the same in the case of quantum as well, except that quantum algorithms typically exploit superposition of states to arrive at the answer. I may also make some, add some statements here. And these are important. Not every problem may have one quantum algorithm that outperform classical algorithms. To tell you that you cannot throw away classical computers, and quantum computers may not be always used. Okay? classical probabilistic algorithms are known to work as efficiently as quantum algorithms in many cases. I'm only saying many cases, not in every case. But there are problems for which quantum algorithms are superior, at least less of. Okay, and that is what actually drives extensive amount of research that's happening in quantum computing. Now, I'm going to describe two simple algorithms, one algorithm, and then talk about two other algorithms. The first one I'm going to talk about a Deutsch algorithm. And the question is very simple. I have a function whose input can be 0 or 1. The output also be 0 or 1. Okay. Now, what are the possibilities? For both the inputs, that is 0 and 1, the output both can be 0. For both the input 0 and 1, the output can be 1. These are called constant function because independent of the input value, the output is 0. And in F2, the output is 1. Both are classified as constant function. On the other hand, you can have F3 of 0 to be 0, F3 of 1 to be 1. And in case of F4, it is the reverse. These are called balanced functions. Balanced in the sense, for half the number of inputs, the output is 0. For the remaining half of the inputs, the output is 1. Which of these half, how do you choose this half? That is decided by the rule that you specify for the function. The question that we want to ask is the following. It is known that the function is either constant or balanced. Okay. The question is to decide whether it is constant or balanced. The question is not to find out what is the output. The question is to decide whether the function is constant or balanced. Okay. If you want to do it on a classical computer, how many operations you may have to do? Let us say I have done the first calculation, you will either end up with 0 or 1. Can I say it is constant? You cannot, because F3 also has 0 as the output. First, okay, and for 1, it becomes 1. So it can change. So I have to do two calculations in order to really figure out how many, two calculations to figure out whether it belongs to constant class or balanced class. How do I do it on a quantum computer? Here is the circuit for it. Now that we know how to understand quantum circuits, I'm not going to spend a lot of time on this. So there is one input which is 0, and there is another input which is 1, and I put Hadamard gate on both this. Hadamard acts on these two respectively, and you will end up with a state which is like this, apart from the overall organization. Okay. And here is a circuit which will actually has the circuitry to calculate the function f itself. So every quantum, every function that you want to calculate, you can design a circuit which will calculate that function for every possible input. So I start with the 0, 0, and I get psi, which is at the after the action of Hadamard gate, which is in this form, and from then it gets into this box, big box, which calculates the function f on this. Okay, and what are the possibilities? I'm saying it is y addition modulo 2. So the plus inside circle stands for addition modulo 2 and the f of x. This is what I calculate, and this is the output that I have. Why this 4 terms in this? Because it's a linear operation. So if my input is a superposition of 4 states, the output will also be a superposition of 4 states, and these are the states. Now let us ask, if the function is constant, say it gives the same output 0 for every possible input. That is, the input is 0 or 1, it is going to give me the output 0. Then you can immediately calculate phi is essentially this. That is 0 plus 1, 0 minus 1. That is what the output will be at this stage. Okay. And if it is 1, that is f of 0 is 1 and f of 1 is 1. Once again, you will see the function or the state that you get at the end of this action of this box QF is 0 plus 1 for the first qubit, 0 minus 1 for the second qubit, but overall there is a negative sign. Okay. What is the difference between the two? The difference between these two is the overall negative sign. The second qubit is in the same state in both the cases. The first qubit is in the same state, but overall negative sign is there when the function takes the value 1 for all possible. What is the other class? The function can be balanced. That is, it outputs 0 for one input and 1 for the other input. In this case, if you go through this process, you will find that the state is 0 minus 1. The second qubit is in the same state as in these cases, 0 minus 1, whereas the first qubit changes its nature depending on whether the function is constant or balanced. So now if we have a way of figuring out the state of the first qubit, whether it is in 0 plus 1 or 0 minus 1, you have answered the question. Therefore, you need to perform only one calculation. I calculated f of x only once using this. I'm not repeating it twice. I'm doing it only once. Therefore, with one calculation, I will be able to tell you whether the function is constant or balanced. What is the role of the second Hadamard gate? As you all know, Hadamard gate converts 0 and 1 to superpositions, and it will convert superpositions back to 0. So when I put the second Hadamard gate on the first qubit, 0 plus 1 will become 0, 0 minus 1 will become 1. And these are easy to detect because it is essentially figuring out whether the spin is up or down. Okay. Now this doesn't look very appealing. Classical computer does 2 and the quantum computer does 1. What is the big deal? Now let us extend this problem. Let us say I have got 4 possible inputs, 0, 0, 0, 1, 1, 0, 1, 1. And once again, the function is either constant or balanced. The question is the same, is the function constant or balanced? Okay. How many classical computations will be required? Minimum 3 computations will be required in this case. If you want to do it classically. In the worst case, it is possible in the very first time you may end up with 0 and 1. Therefore, you can say it is balanced. It cannot be constant because 0 has come, 1 has come. But unfortunately, you end up getting all first 2 times both 0, 0. It could be constant function f1 or it could be a balanced function f3. You don't know. So you may end up doing 3 calculations in the worst case. And what does quantum circuit do? Once again, it's able to do it in just 1 calculation. So you have got a pair of qubits here, 0 and 0, and you have got corresponding Hadamard gates, and you have got essentially the circuit which will calculate it. This circuit, of course, will be able to calculate it on 4 inputs. And of course, there is one additional qubit here, which is in the state 1, exactly like what we had here, 1 qubit in the state 1. And if you go through the process, the way I explained before, you will see at the end of these two, these two Hadamard gates at the output stage, you will end up with the state like this, 0, 0, 0 minus 1, or if it is constant, if it is balanced, it will be 1, 1, 0 minus 1. Once again, you see, if all the qubits, that is qubits on which Hadamard gate acted, which started at 0, if they all end up in 0 after the process, you know the function is constant. If they all end up in state 1, you know the function is balanced. But how many times I calculated? Just 1 circuit to calculate. I'm not repeating it twice to calculate on all possible 4 possible combinations. Now it is easy to generalize this and show even if you have n of them, that is 2 power n inputs, and the function is constant or balanced, then you can show that in the classical case, the worst case, of course, you need to do 2 power n minus 1 plus calculations, but on a quantum computer, you just need 1 calculation to do this. Now imagine n is of the order of 10 or 20. On a classical computer, you may have to do really a large number of calculations in the worst case, whereas on a quantum computer, it is just 1 calculation to figure out. So this is a very artificial problem, but it brings out the power of what quantum algorithms can. Okay. Also recall that how smartly we exploit the possibility of superposition of states in this. Now, this is just to remind you about the RSA cryptography. I'm talking about the next quantum algorithm now. So here the safety mechanism is essentially the time required to figure out the prime factors of a large number. Okay. And classical computers are simply too slow to do it in any reasonable amount of time. Okay. But in 1997, Peter showed an algorithm based on, of course, quantum ideas using superposition and so on and so forth, that you can actually do it in a very, very fast and efficient way. And he was awarded Nobel Prize for this in 1998. Of course, this is Peter Shor who devised the algorithm. This is Peter Shor currently at MIT as a professor of mathematics and computer science. And this is actually the passage from the organization which I've awarded, I think it is a Congress of Mathematicians, if I'm right. While it is easy to make a large number from smaller ones, it takes much longer to find all the factors of large. This time factor is the basis of security offered by any encryption methods, including RSA. Using Shor's algorithm, factorizing large numbers on a quantum computer would be just as fast as multiplication. That means essentially all these cryptographic methods would fail if quantum computers become available for this. Here is a calculation. It's a theoretical prediction, of course, as to how quantum algorithm, which is the Shor's algorithm, and the best known classical algorithm, which is the sieving, will work for a large number. Okay. So if I have a n bit, let us say 100 bits and 1000 bits, you can see that this line here corresponds to which rises very steeply, corresponds to a factorization algorithm due to Shor, and these are classical algorithms. So if you have 1000 qubits, you can see that Shor's algorithm, sorry, it's the other way. The sharply rising ones are the classical algorithms. The almost straight lines are the quantum algorithm. So if I have a Shor's factorization algorithm on a 1 GHz machine, 1 gigahertz machine, it will sort of find out the prime factors of a 1000-digit number in about a few hundred seconds. Okay, whereas for a classical computer operating at that speed, using classical algorithm, it will take about 1 million years. Okay, now you see the problem of the efficiency of quantum algorithms when it comes to factorization method. I'm not describing this method here, it is very involved, but I'm just telling you, if you actually find a computer on which you can implement Shor's algorithm, this is the kind of time reduction that you get. Okay, what is going to take thousands of years on a classical computer using classical best algorithm that we know. On a quantum computer, it will take hardly a few seconds or few tens of seconds. Now, the next one I want to introduce to you is a Grover-Search algorithm. Once again, I'm not going to describe detail. These are a bit involved. The problem is this: identifying a pattern in a long list of unsorted patterns. So if you are given a dictionary and asked to locate a word, it is easy to go because the dictionary is a sorted list. They are sorted in some pattern, some way. Okay. If you have an unsorted list of names, then it's going to be very difficult. Okay. A classical algorithm would require an average about half the number of the size of the list. So if you have a list of length 10,000 and an average, you may require about 5,000. When I say average, it is possible in one case you may, the very first entry maybe is what you are looking for. In another case, it may be the last entry that you are looking for, and an average, it takes about 5,000 checks. Okay. Whereas if you use the quantum algorithm developed by Grover, it will always be square root of n. If you have 10,000, it will be able to tell you whether the sequence is present in the list or not in about 100 days. Okay. 10,000 to 100, 10,000 to 5,000 may not look very appealing, but just imagine you've got about 10 power 10. So you have 10 power 10 by 2 step searches using a classical algorithm, whereas it is, let us say, under root of 10 power 5 for a quantum algorithm, which is much smaller. So that is the kind of speed up we get. It's called exponential speed up, and quantum algorithms can do if you have a quantum computer which can actually implement this quantum computer of suitable size. Okay. So what are the promising architectures to implement or create quantum computers? We have superconducting qubits. We can integrate them and make quantum computers. So the existing computers with IBM and Google and SpinQ, these are all based on superconducting qubits, which if you remember, I talked about Josephson junction. That's what they employ to excel. You have trapped ions, the ion qubit that I talked about. So Honeywell, IonQ, atom computing, they all exploit this, and they also have working versions of quantum. You can have photonic qubits from Xanadu. They have produced about 220 qubits, which you can operate on. And you have topological qubits. Microsoft is pioneering this, but as of now, it looks like we don't have one which is in a working version of the topological qubits. When it comes, of course, it will be a real revolution because topological qubits are inherently protected by something known as decoherence, okay, which is what is actually spoiling everything else that I have spoken about here. Superconducting qubits, trapped ion, both suffer from this, whereas topological qubits will be free of this disturbance from external noise. Okay, so what are the quantum computers that you have? So the one on the left is the ion trap processor, and it holds about few tens of atoms, but you can see the size of this computer. Okay, and it is nowhere near, not even the UNIVAC that I spoke about, but this is the kind of size you need. Okay, the IBM superconducting processor, you can see the arrangement that you need there, and all these arrangements are basically to host the small chip that is being held in hand. So this is where actually quantum computation happens. All this paraphernalia that you have here are basically to cool this chip to sufficient temperature, making readouts and so on and so forth. Okay, and so this is still not in a tabletop form. These are all huge laboratories that you need. Okay, and once again, Google system, which is technology-wise similar to IBM, both are based on superconducting qubits. Once again, it is a chip that you can hold in your hand, but of course, you need a huge laboratory arrangement to actually host this chip to perform computations. Okay, this is where the technology is currently now. Okay, so nobody is expecting that you will have a quantum computer as a desktop computer anytime soon. Okay, now what are the difficulties that we face? There are two major hurdles. One is called decoherence. So we talked about superposition being very vital for many of these quantum algorithms, but a decoherence is a process where the superposition is not stable. It collapses to one of the states because of external disturbance and influences. Okay? And error correction is another hurdle that we need to worry about. What is error correction? I will describe it in a classical context, and a similar idea can be extended to quantum context as well, but I'm going to discuss this. So what is error correction? Let us say there is a circuit and that circuit is reliable, but with a very small probability, it can produce while it is expected to produce 0 and vice versa. It will produce 0 in place of 1 with a certain small probability. So when it is actually done this, you will not know whether it is the answer that you have got is right or not. Therefore, there should be some way of figuring out whether an error has happened or not. If an error has happened, you should be able to correct that error. How do we do that? So that essentially means that it is not enough to have just one qubit to represent a number. We need to have more qubits, because if it is one qubit, what comes out 0 is what you get. You do not know whether an error has happened or not. Okay. So one of the feature or one of the methods of doing this is to represent this using 3 qubits, let us 3 bits, let us say. 0 is represented as 0, 0, 0, and similarly 1 is represented as 3 ones. Assuming that there is only one bit flip that we expect, that is only one of the bits will flip, not all the 3. A binary sequence 0, 1 will now be represented as 3 zeros followed by 3. And I'm going to read the sequence in units of 3. Assuming that there is an error in 0 occurred, that is one of the zeros has flipped to 1. Then it could be either 001, 010, 100. The moment I see 3 digits containing 2 zeros and 1, 1, I know an error has happened, because my 3 digits can either be all 3 zeros, all 3 ones. It cannot have any other combination. So this tells me that an error has occurred, and I also know which bit has. For instance, if I get 001, I know the third bit has flipped. Therefore, I will flip back to 0, and I will continue with the processing of information. So this is the way we correct errors. We detect and correct. This is called error correction. Okay. Quantum error correction is similar but a bit more involved. But key point is, even in the case of quantum error correction, you need more number of qubits to represent one bit. So here, in this example, I have used 3 bits to represent one classical logical bit. Whereas in quantum computing, once again, when you go, there are other methods of doing quantum error correction, but if you adopt this method, you still need more qubits to address this issue. Okay. Now, what are the challenges that we have? Scalability. While we are able to make a few hundred qubits, and as you already know that many qubits are required to represent one qubit to avoid error correction, we need compute architecture which is scalable. I should be able to produce millions of qubits so that I have reasonable number of qubits available for performing computation in a reliable. Error rates, qubit coherence times, these are issues that we need to address. Noise, which you cannot avoid, because the moment you put in more and more gadgets to produce a system, noise is unavoidable. And of course, there's always a gap between theoretical potential, what theoretically one can do, and where the practical implementation of those theoretical ideas. And these challenges also mean opportunities. You can have more stable and scalable quantum system. The development of such systems is an opportunity people can contribute. Hybrid approaches, how to combine quantum systems and classical computing systems to solve complex problems, because quantum systems have certain power and the classical computing machines certain power. For instance, one of the things is memory. Memory is always an issue for quantum computing, because there is something called a no-cloning theorem, which doesn't allow you to make copies, whereas it is much easier to do on the classical domain. So maybe for memory purpose and reading in and reading out, one can use classical computing and so on and so forth. Therefore, how well to combine these two systems to produce a really well as efficient computing system. Okay? Of course, we need advancements in chemical research, material science, and so on and so forth. And these advancements in turn will help us to do better in chemical research, material science, and drug discovery, and so on and so forth, and which are very, very important for quality of life that we talk about. Okay. Now, having talked about these technical ideas, I will say something about research activities worldwide. This is more of a business talk, so I will rush through a bit. So now this is the list produced by MIT in 2022, if I'm right. And you can see the list of giants who are into quantum computing. nations, almost every country is investing in quantum computing, and are also software giants and other corporate houses are investing in quantum computing, because there is a hope that quantum computing will be able to solve really hard problems which are of importance. For instance, drug discovery, material design, blockchain, and so on. Okay. And what about India? Of course, India is not sitting idle. India is making huge investments in this, and here's the list of government company, corporates, and private entrepreneurs who are entering into quantum computing. Now, last few slides I will talk about. So this is next few are slides from the McKinsey's document list 2024 technology monitor. So now you can see the global public investment in 2023. Okay, total is about 42 billion, and you can see China is investing almost $15.3 billion, and India is investing about $1.7 billion. Okay, almost 10 times more than what India is investing. Okay, but investment alone doesn't matter. It also matters what are the results that you produce. And the next slide will actually tell you that. Though China has invested a lot, you can see the number of patents filed that is much higher for United States and Japan, though they have not invested as much as China has invested. Of course, we are not there in the top 10 in this. And what about the number of publications that come from these? Of course, Europe Union collectively, except UK, together they contributed the maximum in terms of number of publications. And of course, India is luckily in the top 10 as far as the number of publications is concerned. And though we are not there in the number of patents filed, definitely we are there in the number of good publications that we have produced by carrying out research within India. Now, why should students like you be interested in this? That is because the market size seems to be looking to explode in the next 1 or 2 decades. So it's expected by 2035, you can see by conservative estimate, a minimum of $28 billion will be invested, and in some optimistic way, it could be all the way up to $72 billion just for quantum computing. For quantum communication, again, you have these numbers 11 and 15, and quantum sensing 0.5 and 2. Okay? And by 2040, just 5, remember 2035 is since 10 years from now, not really far away. By 2040, this almost doubling 28 to 45, 11 to 24.5. So since so much is being invested by companies, corporates, and government, there will also be a lot of scope for students who are interested in pursuing research in these areas. We need human research at all levels, right from people who can create gadgets to people who can develop algorithms, people who can implement, people who can transfer ideas from classical computing to quantum and vice versa. So maybe I think that is where I will close. And the picture here is the computer that was there in last 19th century, which could hardly do multiplication of few numbers, but within a span of about 50-60 years, you know where we are. By 1950, we already had a computer which was much faster than this. So technological revolutions can happen anytime. It's very difficult to predict what technology can do, but if we all can contribute, there will be enough background available for innovative minds to really create wonderful technologies. I thank you all for the patient listening. And of course, I should remember that I should thank Satya as well, but for his Sunday school concept, we would not have so many being trained to take up physics as research and also contribute to education sector in the state. Thank you very much.
Yeah, thank you, sir.
Shari?
Yes, sir. Yes, sir. Great, thank you. So we have received a few questions in the chat box.
Sure.
Maybe.
Can you read out?
Yes, sir. Yes, sir. Please. So first question is, how can we relate qubits with Hilbert space?
Okay, the states 0 and 1 that I wrote, they are actually vectors in Hilbert spaces. So Hilbert space is the mathematical description to describe these states. The states Q 0 and 1 I that wrote, I talked about, they are actually vectors in Hilbert space.
Okay, sir. So then there is a person, Shamjit, asking, what is Qtrit? How it differ from qubit? It is
Qtrit
possibility.
is a system with 3 levels. So people have thought of using 3-level systems and 4-level system to do computation. But as of now, the dominant technology is qubit based. But Qtrit is simply a system with 3 levels.
Okay. So then Sony asked a question, why it is difficult to identify prime numbers?
Okay, this is really a question in mathematics. I don't think I'll be having a quick answer here. Why is it difficult to identify prime numbers? Okay, computer scientists will actually classify it as a computationally hard problem. Okay, because the number of steps to really require. Remember, when I go to 100, I need to find out all the factors that are there up to 50. Or root of 100 up to, okay, that's how we should go. Up to 50, let us say. If I go to 10 power 20, then I need to find out all the factors who are up to 10 power 10, which is a large number of factors could be there. Okay, that's how the number of factors that you need to identify goes. So that is why this is hard. It's a very, very, incomplete answer. But
Yeah.
Excuse me, may I point out something?
yeah.
Yeah, so there is no real proof that integer factorization is computationally hard. It is only true that there is no polynomial time algorithm which would put them in like the NP class, but it's not NP hard or NP complete.
Okay, it's NP class. Yeah, okay, I agree. Thanks.
Okay, so the next question asked by Ayappan Satya is the square root not will reduce classical logic under certain logic.
Sorry, repeat the question.
Is the square root not capital NOT
Yeah, sure, yeah.
will reduce to classical logic under certain logic? Is this the question clear?
I don't think I really understand the question. All the time,
Or
see,
maybe
you cannot have a single qubit, single bit classical gate which will do this.
Shiva sir, sorry for interruption. Okay, I was asking, all the quantum concepts come under certain limits, behave as a classical systems. So, is the square root of naught also works well under certain limits? If yes, then what could be the limit?
So I just have 2 states. How would I even take a classical limit?
Okay.
So usually classical limit is taken in the sense of, like quantum number being very, very high and things like that. So that is not possible in this case.
Oh, okay.
There is no correspondence principle here.
Correspondence.
If you have a large number of qubits, then one can whether classically will the whole system behave, that question one can ask, but not at a single qubit level.
Oh, okay. Okay, thank you. Yeah.
Okay, sir. Yeah. The next question is asked from Raju Dutt. What would be the number of steps required instead of 3 qubit quantum computer if we have a 2 qubit? What would be the number of steps required?
I lost you.
Are you able to hear, sir?
Now you are audible. Yeah.
Yeah. What would be the number of steps required instead of 3 qubit quantum computer if we have a 2 qubit quantum computer for the same?
So this algorithm, I don't know which algorithm you're talking about. If you're talking about a Deutsch algorithm, I have only 2 input, therefore I will work only with the 2 qubits. So under it'll be just a 2 qubit circuit. Under the additional qubit, as I told you, that is always there for every case. Okay. So with the 2 plus 1, 3 may appear large, but when I have 10 qubits, it is 10 plus 1, 11. That's it. So that number, additional 1 qubit will not play a much role. It is basically like a bookkeeping device. So I am not sure whether with the 2 inputs, I can actually encode it using 3 qubits. Maybe there is a way of doing it, but I am not aware. Yeah. But I don't need it to provide any additional efficiency.
Okay, sir. The next question from Manoj Negi. For Dutch algorithm, quantum mechanical realization the circuit seems very cumbersome and would also grow with n too. So is the number of operations sufficient way to decide which quantum or classical would be faster?
So in all likelihood, quantum computers are going to be a bit slow in terms of gate time. So classical, the so-called CMOS technology can switch on and switch off in matter of picoseconds, whereas it may take maybe slightly longer time for qubits of present technology. It might improve. I'm not saying that. Okay. So, but that is sort of, taken care by the way in which it computes the algorithms. So instead of computing one by one, all the relevant outputs for various inputs are computed almost simultaneously. So that's where it gets powerful. So of course you are right. The 100 qubit computer now will cost a few billions, whereas your laptop will cost you hardly maybe less than $1 lakh. Okay, so I'm not comparing in terms of price at all. That is not true. I'm only comparing in terms of power as and when it is realized. But as of now, yes, classical computers would outperform quantum computers in terms of efficiency for the large class of problem that we talk about. And cost-wise, of course, quantum computers are very, very, very expensive.
So there is another question from K. Thirumal Valavan. Is there any quantum computer in India or anywhere in the globe, sir?
To the extent that I know, we have created quantum gates. I don't think we have a working version of a quantum computer as of. We don't have.
Yes. So I think these are the questions. So I request the participants, if you have any specific queries, you can raise your hand and you can directly ask to Sivakumar sir.
Sure, sir. The Ayyappan again.
Yeah.
How to explain the quantum computer for any layman now in simple terms?
So now that I have given the talk, probably you have to do a bit more of reading. So without this technical content, actually, I gave this talk at Anna Centenary Library. If the response was any indication, I think I could actually convey it to people.
Okay.
But yeah, you can see this idea of superposition and how measurement influences the state. These are a bit difficult to comprehend because we don't have direct experience with those notions. Yeah, I'm not sure whether you want to convey the technicalities of this in a simple way. No, but what quantum computers can do, that idea can be easily conveyed. Like the way I showed those graphs about Shor's algorithm versus sieving or Grover's algorithm. Those things can be done and shown that you require so much time on a classical computer. As and when a quantum computer is available, this can be done at a much shorter scale. I think those are the things that will actually capture the imagination of the public, if I'm right.
Okay. Yeah, thank you.
Yeah, Sangeet, you have raised your hand. Can you unmute and ask your clarifications?
Yeah, so I have a slightly technical question. So a few years ago, I think around 2018 or 19, there was a PhD student at the University of Washington, Evan Tang, very famously. So there was this class of quantum machine learning problems, which were, I'm not going to go into the technicalities of which class it was, but she essentially showed very rigorously that the speed ups that like exponential speed ups that were predicted for these class of problems are not actually speed ups but artifacts of the encoding schemes that are being used. And a lot of these algorithms that you see in quantum computing that come up, they very blatantly don't include the encoding and the decoding overheads, and they just talk about the query complexity. And as a result, they claim that there are speed ups, but they might not be. And there is like a very large number of literature that promotes this kind of hype. So, like, what could we as educators and students do to combat this kind of initiative?
So, of course, there is an element of truth in that. If you remember, in one of the I also indicated that in very many cases, when a quantum algorithm was developed, they always developed a classical algorithm which was as efficient as the quantum algorithm or even performed better in some cases, almost everything. But there are cases like, for instance, a factorization algorithm or a search algorithm. These are the cases I'm only talking about in terms of number of steps to complete the calculation. Okay? So where you store, those are all again a big issue for quantum computing. I'm not getting into those technical aspects at all. If you consider all that, yes, it will appear like a quantum computers are not going to be useful at all. But as I told you, it is very difficult to say how technology would develop. Okay, but unless you engage with the technology, there is no way you will be able to develop them at all. So that is the point of view that I take. Yes, some of the points that you talked about are valid, but hopefully they will all be overcome as well.
One more small question, if I may. So I have personally worked on this particular paradigm of quantum computing, which is continuous variable quantum computing, which is some continuous variable quantum computing.
Yeah, CV.
Yeah. So the thing is that it's not very clear to me, because CV, we know that there is a specific encoding scheme by which we can also do qubit-based computation and qubit-based computation over it. So why is this not popular at all compared to like the traditional qubit-based computation?
So I have a feeling that it's a technology that we need to worry about. Okay. See, when in case of 0 and 1, these are distinguishable states. Okay. To the extent that I understand, I know when you have continuous variable, these states are not separated. Like you have a continuum of states, and so when it moves, when it evolves, it will be very difficult to actually distinguish between two states whether it is evolved or not. That is one of the issues. And second thing, we also need a technology where these qubits should be able to sort of interact with each other, because finally I have to evolve these qubits to perform certain calculation. So in the case of continuous variable, I think that my knowledge is a bit outdated. I think there were problems in the initial stages. People have spoken about using anharmonic oscillators, coupled anharmonic oscillators to do this. But yeah.
Thank you.
Yeah, Subhashi J, you may ask.
Sir, voice is very
ion
garbled at
trapping method. Sir, it is okay now?
Yeah, it's
Is it okay? Sir, I have read some news where in Pune they are trying to develop some ion trapping method to measure time precisely, where the time is measured using the transition states between up and down. So is that similar to the technology that is being used in quantum computers? So like, is ion trapping is the same thing? Is it the same thing?
Ion trap is the same, but the measurement of time is actually precedes the quantum computing ideas. So atomic clocks were made much before, and in fact, the technology that is currently being used for quantum computing is borrowed from that. So CCM clocks you might have heard of. Hello?
Now they are trying to make it much more precise. Maybe some
that effort will continuously go on, but I am saying that that probably has nothing to do with quantum information processing.
Instead of the ion trapping thing.
Ion trapping techniques are yes.
Okay, so I think Devanjan Rai.
Thank you, sir.
Devanjan Rai.
Yes. Good evening, sir. Hello?
Good evening, yeah.
Yes, sir. So I raised a question in the chat. Can you hear me, sir? Hello?
Yeah, you read it. You read Devanjan Rai.
The question is, instead of encoding classical information in quantum states, can we encode information in quantum gates? Because the context here is, you mentioned the dense coding, right? So in dense coding, we have 4 outcomes of an event. So we encode the 4 outcomes of an event in identity gate, X gate, Pauli X gate, Pauli Y gate, and Pauli Z gate, right? So we can encode information in 1 qubit gates. That's my question. Instead of encoding in states.
Yeah, but in 1 qubit, you can encode only, what do you mean by how do you encode 4 different, let us say, let me say those information that you wanted to encode are called 0, 1, 2, 3. How do you encode 4 of such pieces in 1 qubit?
No, not in 1 qubit, sir. I'm saying in quantum gate, like Pauli X gate, Pauli Y gate, Pauli Z
They are
gate.
single qubit gates.
Yes, I want to encode information, classical information, 4 outcomes,
Okay.
0, 0, 0, 1, 1, 0, 1, 1, in 4 distinguishable gates.
But then you have 4 of them. That is as good as having.
So that's what we do in dense coding, right, sir?
No, in dense coding, I have only 2 coins.
Yes.
I don't have 4 coins.
No, I have 2 coins, 0, 0, 0, 1, 1, 0, 1, 1.
Exactly, yeah.
2 bits of information.
Yeah.
But I have 4 gates, right?
Hold on. I can send only 1 coin across to the other person.
Yes, sir.
Yeah.
Yes, sir. But in order to decode, I have to I have to just encode using I have the Bell state shared between Alice and Bob.
If you have Bell state, you can do. But I'm saying, let us say you have like classical case, let us say I have 0, the other person has 1. Whatever you do to 0, you will not be able to convey all the 4 pieces of information.
No, in dense coding, we have Bell state, right? In dense coding, we have maximum entangled state shared.
Yeah, correct.
So, and according to the outcome of the event, I manipulate the Alice manipulates her qubit using identity sigma x, sigma y, or sigma z, right?
Okay.
So the encoding is in the gates.
Encoding is in the state. The state carries the information. I make some change to the state and share that coin with the other person. So that other person now makes a measurement and figures out what is the state of the combined system. So from that, the second person infers. Yeah.
You can also map from the state to the gates, right? From the state.
You can. That's true.
That's what my question is. That's what my question was, sir.
So, but remember, you are basically trying to send the qubit, not the gate.
Yes,
Gate is the process, as I told.
Well, thank you, sir. Thank you, sir.
Yeah. So the last question, maybe we will restrict with this last one. Yoga Lakshmi asking, sir, as I want to start from the scratch to get a better knowledge about quantum computing, from where I have to start, sir?
Say start basic quantum mechanics is something that you need. And of course, the relevant mathematics, like, a brief introduction to linear algebra, some complex numbers. But you can do a lot with that. And there are excellent books and lecture notes available nowadays. Lecture notes and books at all levels, very introductory to very advanced.
Yes. Yeah. Okay. So I think we will close the Q&A session because already time is 7:50. So suppose if you have more questions, of course, we will share Professor Sivakumar's mail ID. We may directly ask so that he may be able to answer some detailed queries. Yeah. Okay. So I think, so at the outset, I profusely thank Professor Sivakumar for giving a wonderful, really very beautiful presentation. In fact, he started from the very basic. He explained the difference between the classical and quantum computers and what is the difference between classical bit and quantum bit. Also, he touched upon, not very detailed because it's a kind of popular level, he touched on all the different algorithms. And also, he gave a nice overview about what are the current status of quantum computing in the world and also in India. And he gave a nice answers to all the questions asked by the participants. I'm sure this talk would have been a kind of wonderful starting point for the to learn the quantum computing basics. I request the participants also, you can share this lecture. The lecture is also available in the YouTube live. You can share the lecture to your fellow friends also, whoever needs this. And I thank our other organizers like Dr. Yes, sir.
I just want to say, since there are so many comments in the chat box about the good books, Preskill is a great place. Nielsen Chuang are great. But if it's very elementary, actually, I will suggest there is a book by book titled Explorations in Quantum Computing by, I think, Williams and one more person. Very elementary. If you know basic quantum mechanics, you should be able to do that. So the title of the book is Explorations in Quantum Computing.
Okay, sir. It's nice. Thank you. We will share this book to participants. We have so many WhatsApp groups. Definitely, we will share the information. Yeah. So then we want to thank the other organizer like Dr. Kamal. He constantly supporting me and supporting the Sunday class to carry on further. And I thank our Rajmohan for giving an introduction, and thank Radha Ritish Bharat for giving this introduction about our Sivakumar sir. And I also thank all the Sunday class senior students for supporting us. And also I thank the participants who are really stay with here and really ask all the questions and passionately listening to the lectures. And the last, I really thank from my deep of heart of Satya sir. So he will be there forever. We will remember him forever. We will carry out his legacy and mission and his passion of physics teaching. Thank you, one and all. Thank you, sir. Great. Thank you, sir.
Can leave now?
Yes, sir. Please.